So this is the last lesson in the unit on just working with derivatives. And essentially after this lesson, we should, theoretically be able to differentiate any sort of equation or relationship or function that you've seen or ever worked with in math class until now. And this last section is really, as it says here, focusing on the derivatives of logarithmic functions. Now, hopefully in class we have time to look at some group problems that prove some of these things, but right now these three statements are just true, and these are the last three things we want to remember. First of all is a sort of a definition of the number e involving limits, and e is the limit of 1 over 1 plus x to the power of x as x approaches infinity. And we've seen that before, actually. The derivative of the natural logarithm is 1 over x. Then I have a little statement here where x must be greater than 0. And that's just quite simply because a logarithm, any logarithm, the input of a logarithm must be a positive number. The logarithm of 0, any logarithm of a negative number doesn't make sense. And so if you were to visualize the graph of the natural logarithm, it would be congruent to the graph of 1 over x, but only half of it, only the section where x is greater than 0. The natural logarithm doesn't exist when x is negative. And lastly, what if it's not the natural logarithm? What if we're dealing with any other logarithm? Well, the derivative of any other logarithm, of, in this case, base b, is similar. It's 1 over x, but the denominator is multiplied by the ln of b. And so notice, as with dealing with exponential functions, when we're differentiating, if you have an exponential function that's a base of e, it's easier than if you have an exponential function that's some other base. Same thing with logarithms. The derivative of the natural logarithm, again, is just 1 over x. And so if you're dealing with any other logarithm, any other base, it's similar, but it's not quite as simple. All right? And so hence why exponential functions of a base e or a logarithm of base e are so useful and so pleasant to work with in a calculus class. With that said, the focus of these notes is just to work with this in a variety of examples. And I want to start with something called logarithmic differentiation, which is using logarithms to differentiate something. Now, if you look at this expression here, this is not an exponential function. An exponential function should have a constant base and a variable exponent. This has both the same variable in the base and the exponent. So it's exponential-ish, but this is not an exponential function. So I can't differentiate this treating it as an exponential function. So how can I differentiate it? Well, using logarithmic differentiation. And the idea behind this is before I start trying to differentiate anything, I want to log both sides. And I can choose any logarithm I want. In a calculus class, it's probably best to use the natural logarithm. So I'm going to find the ln of y, and that's going to equal the ln of 2x to the power of x. OK, what's the purpose of that? Well, I don't want to start differentiating yet. The purpose of that is that I can now use one of my logarithm laws to eventually get this exponent of x out of the exponent. I can't yet, though. One of our logarithm laws, the power law, is if you have everything in a logarithm raised to a power, you can write that power as a coefficient. However, if you look in this logarithm right here, not everything is being raised to the power of x, only the x's. Now, if there were brackets around it, then I could just take this x right now and bring it over. But there's no brackets, so it's wrong for me to do that. So how can I eventually get that out? Well, it is 2 times x to the power of x, so I can use a different logarithm law. And that's the product law of logarithms, and that if you are multiplying factors inside a logarithm, you can write it as a sum of 2 separate logarithms. So looking at the right-hand side, I can rewrite this as the ln of 2 plus the ln of x to the power of x. On the other side, I'll just leave this as the ln of y. So now I can use that logarithm law, the power law, and now I can rewrite this. Notice I still haven't differentiated anything. Write this the ln of y equals the ln of 2 plus x times the ln of x. Now at this point I can differentiate. And I'm still trying to find dy dx. Notice I have an implicitly defined equation here, so we'll use implicit differentiation. But now I can actually differentiate this. So now I'm just going to make a little note here. Now I want to find dy dx of both sides. Or actually, I really should say I want to find d dx of both sides. All right, and so I will be kind of thorough here. And so I'll just kind of show d dx, d dx, Maybe I'll kind of squish that in here. All right, so I'll go from left to right. The derivative of the ln of y with respect to x. I have to use the chain rule here. My outside function is a natural logarithm. My inside function is y, which is a function of x. And so the derivative of the ln of y is 1 over y. That's kind of what we saw from today. Times the derivative of the inside function is y prime. All right, next I have the derivative of the ln of 2. Well, keep in mind 2 is a constant, and so the ln of 2 is some constant value, some irrational number. But who cares? It's a constant, and the logarithm of the derivative of any constant is 0. And next I have the derivative of x times the ln of x. Well, for this I have to use the chain rule. Sorry, not the chain rule, the product rule I meant to say. Because I have a linear function times a logarithmic function. And so when I differentiate this, the chain rule, the product rule, the derivative of x is 1 times the ln of x plus the other way around, x times the derivative of the ln of x, which is 1 over x. So let me clean this up. I'll write this as y prime over y on the left-hand side and just ln x plus 1. Well, pretty much done. Multiply both sides by y, and I'm still very close to being done, but I'm not completely done. And it's because my derivative right now is with respect to x and y. And we dealt with that a lot with implicit differentiation, but that was when we were dealing with things that weren't functions. That's when we were dealing with equations that themselves were expressed in terms of x and y. If you look at my original equation, this is an explicitly defined equation, which means I don't really have to have my equation represented. I don't have my derivative represented in terms of x and y. So I'm not wrong, I'm just not done. And so how can I do that? Well, I got to find a way to rewrite y in terms of x, which is quite easy to do if we just look back up, and that's what we see stated here. Y is the same as 2x to the power of x. And so once I remember that, then I'm done. So y prime, or I'll just write dy dx, is 2x to the power of x times the ln of x plus 1. Those brackets there being really important because 2x to the power of x is being multiplied to all of that. And there's my derivative. So notice I used a whole bunch of things from this unit. If I look at all our work here, I used, logarithms. That's from, I log both sides and use logarithm laws. That's from pre-calc 12, really. But I use implicit differentiation, the chain rule, the product rule, the derivatives of logarithms. All those things are kind of used here. OK, so now in general, I just want to work with through various functions, differentiating them involving logarithms. I believe everything is going to involve logarithms here. At some point, everything will involve logarithms today. OK. Sorry, just looking ahead here. So let's do these one at a time. Let's differentiate the ln of x squared. And so I have to use the chain rule here. My outside function being the natural logarithm, the inside function being the quadratic function x squared. But I don't need to do anything terribly complex here. I don't have an implicitly defined equation or anything. So the derivative of the ln of x squared is 1 over x squared. That's my first step, times the derivative of x squared, which is 2x. And now clean this up a bit. I have 2x over x squared, which I can definitely simplify down to 2 over x. OK, that's it. Well, that is totally great. That's my derivative. Something else I could have done, and once dealing with logarithms, we have options. We could use logarithm laws. So I'm going to show another way that's not inherently better, but another option that you may have already thought about. And so let me just go back and rewrite the original equation again. What I can do instead is I can use a log law first. And I can use my power law, which means I can take that power of 2 and write it as a coefficient before I differentiate things. And that 2 is now just a coefficient. Now notice if I differentiate this equation, if I find the derivative, that 2 is just a coefficient, so that's, I don't have to worry about that. All that's left is really what's the derivative of ln x? Well, it's 1 over x. So of course I get the same thing. And one's not inherently better than the other. You may find one simpler than the other. The idea is they're always correct. And as always, we have options. And quite often, we've seen this lots already in this unit, when differentiating something, quite often it's actually not a good idea to just jump straight into differentiating. Quite often it's better off to do some sort of algebraic work using things we've learned about from previous courses before we differentiate to get into a form that's easier for us. So similarly, if I look at this one here, and maybe at this point, I would recommend you just kind of pause the video and try this on your own. But again, I will work this out in 2 different ways. And so for this, one way I can do this is first to, well, in fact, either way I want to do this, I'd rather write that power of, so I'd rather write that root x as a power of 1/2. So I'm going to rewrite this as log base 5x to the 1/2. That's it. One way is to use that chain rule again. This time I have log base 5 though, not log base e. All right, so when I differentiate this, first I need to differentiate the outside function, which is log base 5. And the derivative of log base 5 is still, well, let's say it was log base e. Let's say it was the ln of x to the 1/2. The derivative of that would be 1 over x to the 1/2. Well, it's not log base e, it's log base 5, so it's the same thing, but my denominator is times the ln of 5. So I'll write this as 1 over root x times the ln of 5. That's the first part of the chain rule. Times the derivative of the inside function, which is x to the 1/2. Use the power rule. So that's 1/2 times x to the negative 1/2. And if I write it like this, I can now, and this is, while this is correct, this is definitely needlessly messy. If I write this without negative exponents, writing everything as a radical, in my denominator I have the ln of 5 times root x times 2 times another root x. Write this right here, coming the same as all of this. And then I have, 2 root x's times each other. I might as well write that as just x. So I can simplify this down to 1 over 2 ln 5, or actually I'll write it as 2x times the ln of 5. Okay, so notice most of my work was actually dealing with simplifying. And this is if I use the chain rule right away. It's a little bit messier because I'm using a logarithm that's not base e. But really the only difference is because it was base 5, I have to multiply by the ln of 5 right there. All right, or though, like before, let me see if you like this better. I'll use a logarithm law first before I differentiate anything. So or, I'm going to go back to this. I'll go back to the form where I have the radical written as a exponent. Okay, or I can use a logarithm law again, the power law, and take that 1/2 and write it as a coefficient. And there's a decent chance you will find what I have here easier to differentiate than what I had before. So now I want to differentiate this. So that 1/2 coefficient times the log base 5 of x, well, that's just 1 over x times the ln of 5. Which, notice we get the exact same thing we had before. In this case, I actually definitely, before, if I kind of zoom out and look at all this together, for the question on the left, whether the first example, the second example, one's not clearly simpler to me, but if looking at the second one, I do think the second one I went through was a little bit easier, although it's all the same thing. All right, second last question. Differentiate this. And again, I would recommend you try this on your own first before you watch me work this out. All right, so notice Notice I have something here that's not an exponential function, but it's exponential-ish. It's similar to the first example we worked through today. So this is a great example where we want to use logarithmic differentiation. Which means, before I try differentiating anything, let's use logarithm laws to get to a point that I no longer have, in this case, that cos x in my exponent. So let's ln both sides. So I have the ln of y. And again, I can pick any logarithm I want, but when differentiating, the natural logarithm is definitely the best choice. Now I can just use that power law right away and rewrite this as the ln of y equals cos x times the ln of x. All right, now I'm at a stage where I can differentiate quite quickly, so now I'm going to differentiate everything. And so I'll differentiate this side, and I'll differentiate this side. So on the left-hand side, again, I have y, which is a function of x, and so I have to use the chain rule. First, the outside function, the natural logarithm. The derivative of that is 1 over the input, in this case y, times the derivative of the inside function. On the right-hand side, I have to use the product rule. So I have a product of cosine and the natural logarithm. The good thing is each of those individual functions are quite straightforward. So the derivative of cosine is negative sine x times ln x left alone, plus the other way around. Cosine left alone times the derivative of ln x, which is 1 over x. Now it's really just a matter of cleaning this up. A few things I could do here. Doesn't really matter too much. I'm just going to kind of clean up the right-hand side a bit. I'm going to write this as cos x over x minus sine x over times ln x. And if I just put y prime here, I can do that if I just multiply both sides by y. And again, that y there is up here, clearly stated equivalent to x times the cos of x. So my last step is to substitute that y at the end, or at the beginning. Doesn't really matter where I write it. Maybe I'll write it at the beginning. So x times the cosine of x all times all of this. And that's my derivative. And that leads me to the last example of this unit. Notice again, it's rare for any of these questions not to involve the chain rule or other rules at some point. And really so much of this, yes, is about the rules and working with the derivatives from this unit, but so much of it also deals with things from previous math courses. Logarithm laws and just how to simplify algebraic expressions and working with expressions. That's really the majority of our work is not just the actual act of defining that first derivative. Either way, though, this is the last question. And like before, I recommend you try this on your own. But it is an explicitly defined equation, y equals root 1 plus the ln of x. And I'll work through this in just a moment. So the first thing I would do when dealing with a radical like this is write it as a power. Because then we can use the power rule at some point. OK, now I want to differentiate this. So when I find the derivative of this, I need to use the chain rule, not surprisingly. And so when using the chain rule, the derivative of the outside function, which is the radical, or power of 1/2, I can use the power rule. Leave the inside part alone. This is now negative 1/2 times the derivative of the inside function. And the inside function, I have the derivative of 1, which is 0. I don't really need to write that down, but I will for a moment, plus the derivative of ln x, which is 1 over x. All right, so I'm done, technically, but I want to clean this up. And so what do I have here? I'll write this as 1/2 times 1 over the square root of 1 plus ln x times 1 over x. That's really what we have here. If I look at these like this. And then, yeah, no point leaving it like that. I have 1 over, I'll write it as 2x times the square root of 1 plus the ln of x. All right, so by completing this unit, let's not lose sight of what this unit was about. This unit is about primarily just calculating. It's a process. More so than any other part of this course, this unit is about understanding the processes of differentiating. And it's quite often, it's fairly quick, but quite often it's not. And there's a lot of algebraic steps. And it relies upon connecting to so many things from other courses, especially exponent laws and understanding radicals and simplifying algebraic expressions and logarithms and everything. This is why we had so many courses, so many pre-calculus courses to get to a calculus course. There's a fair amount of background we have to not just learn, but we have to use frequently. And it takes time. The good thing is the more you practice these things, the more you kind of ask questions about these things, the more you solidify your understanding of these previous concepts from other courses. But that completes this unit, in terms of notes at least.